So tomorrow you'll be taking the part one, guys. This is the part one test the part one test for chapter 3. Now, what we're going to do is we're going to split this chapter into two parts. The first part is it's actually a good place to end, so I'm actually glad we're getting to do this because of the way fall break was falling. To do the last part would have just been a little bit too much, too far of a distance for you guys to remember all of this stuff, come back, learn a whole new topic, and then test on this stuff. So it actually fell just perfectly for it to test this way. So what we're going to do is we're going to cover the test objectives. A lot of this stuff is kind of common sense. We've covered it twice now because a few of these questions were on your benchmark. So again, if you will go along with the test objectives, it shouldn't be that complicated. A lot of this stuff is very basic, very common knowledge, and it's just you applying it, okay? So the first bullet says, understand the definition of the law of conservation of mass and how to apply it. Now, before I say anything else, if you're watching this at home, please pause this. I'm going to go pretty fast with the first part. So conservation of mass, very basic, very simple. What you start with, you must end with. Another way to think about it, if I start with 100 grams of salt, now, am I going to end with exactly 100 grams of salt per se? No, because if it's a chemical reaction, it's going to change, right? But do I have to end with 100 grams? Yes, okay, of something. We don't know what it's going to turn into, but it's got to at least be 100 grams of something. So what you start with, you must end. So really what you put in, you must get out. Same way. Now, this applies to key here, the mass and energy. So it's not just mass, but I also want to kind of throw that in because it has to make sense as well. If I start with 100 joules, I've got to get out 100 joules. Can it change forms? Yes, it can turn into cold energy. It can turn into hot energy. It can turn into electricity. It can turn into potential energy. It can turn into kinetic energy. It's all kind of different things. Now, finally, make sure you know this little bullet right here. Basically, what this says is if I have salt and water, is all of a sudden some mercury going to show up? No, that makes no sense. So you can't just all of a sudden create something in a reaction if it's never been there before. It's not just going to magically appear. Just like you can't take something and destroy it. Okay, you can't literally just get rid of it. It's not going to disappear. So that is the conservation of mass. Any questions there? Okay, the next bullet. Be able to distinguish between the law of definite proportions and multiple proportions. Okay, definite. If you're looking at definite, this is the definition. A chemical compound with the same elements are the same proportions by mass. Okay, let me explain that. Do you agree that water is a chemical compound? Okay, if I have one water molecule or a million, will all of them be H2O? Yes, chemical compound with the same element are the same proportions by mass. Will every water molecule weigh exactly 18.02 grams? Yes. One's not going to weigh 19, one's not going to weigh 17. Every one of them will be 18.02 grams. Now, let's get into why that is the case. Hydrogen. Will hydrogen's mass ever change on the periodic table? No, it's always going to be that number. It's locked into place. So if I'm looking at a water molecule in my left hand and a water molecule in my right hand, will the left one have a hydrogen weight of 4 and the other one have a weight of 1? No. So it's got to be the same mass by proportion, right? Just like every oxygen. Does anybody remember what oxygen it is? 16. Very good. Every oxygen, whenever you look it up, it'll always be 16. So every time you have a chemical compound with the same elements, it'll always be the same proportion by mass. Does that make sense? I need a yes or no. Yes. Very good. Multiple proportions. Okay. What does multiple mean? Many, 2 or more things. So 2 different compounds. Does it just have to be 2? No, I can write 13 different things down here. But the key here is that they are different. But here's another concept. But they have the same elements. The 2 examples I give you, carbon monoxide and carbon dioxide. Are they 2 different compounds? Yes. But are they composed of the same elements? Yes. Well, here's what I need you to know. If you read the definition in your notes, it's long, it's complicated, it's drawn out, it's a pain in the butt. Here's the connection point I need you to get. It has small whole numbers whenever you try to relate their masses, okay? So again, just know that the multiple is 2 different compounds, same elements, and they have small whole number ratios. Any questions? Okay, all right. Next bullet. Dalton's atomic theory. Very important. Make sure you circle this. You need to know whose. That's why I underline this. It's Dalton's atomic theory. Make sure you know who it is. Now, he said 5 things. Now, what do you think the T, F, and F are on the left? True and false. You have to know true or false. I'm just going to tell you now. There are 5 questions on the test tomorrow that deal with this. So I would recommend you knowing it. Here's how it's going to ask. It's going to say, is this a part of Dalton's atomic theory? Yes or no. And you'll look and you'll find the one that is. Or it could say, which of the following is not a part of Dalton's atomic theory? You'll have to find the one that's not. Then it may ask, which of the following do we believe today? Okay, well, you're going to find the one that is what? True. It may ask, which of the one do we not believe today? So you'll find the one that is false. Does that make sense how those are going to be asked? So you're going to need to know what the 5 are and then if they're true or false. There are 5 questions, so make sure you know these. So, all things are made of atoms. Is that obviously true today? Yes, we know that things are made of atoms. The second one, all atoms of the same element. Okay, the exact same element. So let's just talk about oxygen. All atoms of oxygen have the same size, same mass, and same properties. That is false. Now, some of these we know about. When it's a different mass, what is it called? An isotope. Now, what does an isotope have different numbers of? Neutrons. Now, this is all in front of you. But I want to know, would you have known that if that was not in front of your face? That's what I need you to be able to tell me, okay, I see it, and I can read it to you, but I want to know if you know it. That's the key. If it has a different mass, it's called an isotope. Well, the reason it's an isotope is because it has a different number of neutrons. This word we haven't focused on a whole lot. We've talked about it once or twice, but I haven't really zoned in on it. Size. Let's talk about this for just a second. That's not what I want. Actually, I need this. Nope. Hold on. Let's go here. Then this. Okay. So if I take a hydrogen atom, okay, that's not what I want to do. Tell you what, let's do. I'm trying to think of the best way to explain this. Give me just 1 second. I hadn't done this one yet. Okay, here we go. This is a good way to explain it. All right, if I take lithium, okay, do we agree that lithium has 3 protons? Okay, if you look it up, it's number 3. If it's neutral, how many electrons will it have? 3. All right, so 3 electrons. Now, remember these things? What is that thing where electrons run around? Orbitals, very good. How many's in that first one? 2. 2 electrons, right? What's going to be left over? 1 electron. So, now, if all of a sudden I take this, and I take this electron, and I get rid of it, first of all, will this thing become positive, or will it become negative when you kick out an electron? Why is it positive? Very good. So that's going to change to 2, so that means you have 1 more proton. So you agree this thing's going to be positive. Will the size change? Yeah, it will, because you're going to take that whole ring and get rid of it, right? So it's going to be 2 rings, and now all of a sudden that ring is gone. Did it get smaller? Sure did. So an ion makes things get smaller, or depending on if you're adding or taking away, right? So that's what we're looking for. So again, that's how we can tell that ions. So was that kind of a good example there? All right, very good. So now, ions are not on the test, but we will talk about these later. You're going to have to know these little letter dates. You might as well kind of go ahead and commit to knowing it now. So an ion has a different what? And it's because it has a different number of, just like you just saw, you can take them in, you can add them off, okay? And then that is false, and because they have different sizes and different masses. Most of the properties are going to be the same no matter what they are, because they're going to act the same no matter what their size is or the mass is. They'll act the same, though. Okay, the next. Atoms cannot be subdivided. Well, that's false, because things that are smaller things in atoms? Yeah, well, protons, neutrons, electrons. So it can be subdivided. They can be created. Prime example of how they can be created. If you will look right here on the periodic table, look at all of these right here. What do you notice? Hollow. They're hollow, just like that one, all of those. And what did it say when they were hollow? They're man-made. Was that created? Absolutely. So they can be created. And then finally destroyed. Remember, Farley takes what atom and splits it? Uranium. They take uranium and just knock that sucker apart and get a whole lot of energy. So this was false. He was wrong here. So the next one. I think early 1800s. I think. I need to double check that. I'll look into that. I think it was early 1800s. Though. No. But yeah, this was all before that. But I'll double check that whenever y'all writing. I'll look. Okay. Number 4, atoms combine to form compounds with simple whole number ratios. Point being, will you ever see a decimal in a formula? No. You will never ever see this. H. That's not what I want. H 1.290. Right. That'll never happen. So again, we need small whole number ratios. And finally, in a chemical reaction, atoms are combined, separated, or rearranged. That is also true. So make sure you know those 5. Okay. The next bullet. Know the cathode ray, who did it, and what its significance was. Okay. Please don't mess that up. Very simple. Cathode ray was J.J. Thomson, and that discovered the electron. This was your modern day neon sign, if you will, essentially. Remember, because they had the little gas chamber, and they put electricity, and the electricity kept flowing through it. Gold foil. Rutherford. It discovered the nucleus. Now, I know we haven't said this one, this weird thing right here, this plum pudding model. This is what Rutherford said an atom looked like. He said it was this little ball, okay? It was literally a ball, and it had all these electrons stuck on the outside of it, okay? So imagine a beach ball with a bunch of little things stuck on the outside of it. Is what he thought atoms looked like. Is that true today? No, that's definitely not right. But again, for what they had technology-wise back then, that was a kind of a decent idea, I guess, if you will. Okay, so gold foil Rutherford plum pudding model. Again, you won't have to know that, but it helped discover the nucleus. Now, what holds that nucleus together? Okay, so the nuclear forces hold the nucleus together. Somebody asked me earlier, why aren't electrons on this list? Why are they not listed? They're not in the nucleus. Electrons. So what are the only 2 things in the nucleus? Well, Well, there's a force between protons, neutrons, and a neutron. Now, these are not the same thing as IMFs. What is an IMF? Intermolecular. Is an atom a molecule? No, it's not. An atom is an atom. Atoms make up molecules. Okay, molecules are much, much bigger. Thousands and thousands of atoms put together. This is the thing that holds the nucleus of an atom together. It's just that force. Because remember, this thing is so small, gravity can't affect it. That's why it's able to hold itself together like that. Okay? Next, really, I should not even have to tell you this one. Know the charges of all the subatomic particles. Protons are positives, neutrons are donuts, and electrons are negative. Okay? No, I'm kidding. It's neutral. Okay? Make sure you know that. What? It does look like a donut, but it's neutral. Next, the unit of the atomic radii. First of all, atomic radii. What does that mean in layman's terms? Very good. Let's add that, okay? It is half, well, I'll tell you what, no. It is distance from center of the nucleus to the outermost orbital. Okay? The distance from the center of the nucleus to the outermost orbital. Now, remember how we have this chart back here on the very back on the wall? Okay, what do you notice as you go down the column? They get bigger, but left to right, they get smaller. Okay, we're going to talk about that. We're going to talk about why they get smaller. But bigger is because orbitals expand. Smaller is because they're the same size orbital, but they get closer together. We'll get into that, okay? Now, the unit is the picometer. Now, this 1.0 times 10 to the negative 12 is how small that picometer is. I just wanted to show you where it stands in terms of the metric system. In your notes, and I knew I forgot this, and I looked it up and I was like, I knew I was wrong. I forgot the nano in the notes. So in your notes, you may actually, if you wrote that down, the N is missing. So this little funky looking U right here is micro. Okay. And when you think of micro, think of microscopes. That's what cells are measured on. It's 1.0 times 10 to the negative sixth, and the nano is 9. That's like a nanometer, really, really tiny things. Okay? Yep. All right. So this is where you need to catch up with. Okay, so the atomic number. Okay, whenever you're thinking of the atomic number, this is one of the most important concepts in all of chemistry, just the very basics. It is your number of protons. Extremely important because this identifies the element. So if I asked you what is element number 10, well, how could you figure that out? Well, you look on the periodic table and find number 10. Does anybody know what it is? Neon. Very good. So it is neon. And that number tells me the number of protons. So again, the atomic number is very, 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 very vital. There are a lot of questions on the test dealing with this and being able to determine and being able to figure it out. You will have a periodic table on your test. Okay? So you will be able to do that. Now, it identifies the element, and here's the deal. It will never change. So if I'm talking about neon, neon will always have a number 10. It'll always be 10 electrons. Can the neutrons change? Yes. Can the electrons change? Yes. But can the proton number ever change for that element? Never, ever, ever, ever. Do not ever change the number of protons for that element. Okay. The next one. What is an isotope? What is an isotope? Okay. Yep. So it's just a different mass because it has a different number of neutrons. Now, I know in the test objectives it says how to identify one. That's just you being able to look at the masses and being able to figure out what it is. Alex, did you write this down? Okay. So again, it's an isotope, different mass, because it has a different number of neutrons. And again, normally the neutrons are going to be higher than the protons, and we'll see that in just a second, okay? Everybody good here? Good, okay. Next, what is the mass number? Okay, so atomic number tells us the number of what? Protons. The mass number is a little bit different. The mass number is the number of protons plus what? Neutrons. Very good. Now, I've had all people all day kind of first period say, well, wait a minute. What do you mean it's a whole number? Thought it was a decimal. No, you don't round. Okay? Because can you have half a proton? Can you have a quarter of a neutron? No, you can't. Okay? It's an all or nothing thing. So the mass number is a whole number. Well, here's the difference. The mass on the periodic table has a decimal because it's the average atomic mass. And we're going to see the average atomic mass in the next slide. So just kind of hold on to this concept of the reason it's a decimal on the periodic table is because it's the average. Okay? Because you got to remember that not every atom of oxygen is always identical, because what can change with every oxygen? It's neutrons. Very good. Which also affects the mass. Very good, Jonathan. Very, very good. Okay. So again, the reason it's not a whole number is because of that average fact. Now, and again, this is just kind of a concept. Remember the worksheet we did yesterday? When you looked at most of them, were the neutrons ever the same as the protons? Normally, they were a lot different. Normally, the neutrons will be higher. Now, that won't always be the case, but for most cases, it will be higher. It won't be like crazy higher, but I mean, there are some that are 40, 50, 60 neutrons higher. Because think about it. The neutrons only add mass and take up space. That's all they do. That's the only thing a neutron will do is add mass and take up space. So that's why we do not have whole numbers on the periodic table. Thanks, sir. All right, everybody good here? So, the next bullet, it says, know the standard that all atomic masses are compared to and what it is equivalent to in AMUs. Okay, remember how we have this standard. Okay, the way I talked about this was the density. What is the density of everything compared to? What is density always compared to? Water, right? Okay, so water is what is compared to density. What is the density of water? 1. Okay. Well, when they started saying, okay, we need to be able to mass these things out. How can we tell the mass of an element? What they did is they went outside. Okay, not literally. They just kind of did this. And they dug up a carbon-12. I mean, you can. They just had one. They went to their lab and picked it out or whatever you want to say. Okay? So they had a carbon-12 atom. Now, since it is carbon-12, this 12 tells me it's the mass number, right? Okay? So this 12 right here tells me it is the mass number. Again, how do we solve for mass number? Plus neutrons. All right. Now, carbon is always going to be number what? Carbon's always number 6. Well, that tells me I have 6 protons. Well, if it's a mass number of 12, that means I have 6 neutrons. Got to be true, right? Well, what they did is they put this one carbon atom on a scale. And the scale just showed up blank. And they said, okay, we need to make this scale show something. What they did is they said, well, since it's carbon-12, we're going to make the scale show exactly 12. So they turned a little dial and said, okay, this thing weighs exactly 12 AMUs. And what is an AMU? Atomic mass units, okay? Now, this is not grams. If you put one atom on a scale, is it going to weigh 12 grams? Absolutely not, okay? Lot smaller. But then what they did is they allowed everything else to be compared to this. So when they put a carbon-13 on there, what did it weigh? 13. Carbon-14 weighed 14. And everything else was based on this factor right here. So the scale was set around this carbon-12 atom. Now, why did they pick that one? I don't really know. I just know it's very abundant. Y'all remember the percentages? It was like 97%. Okay, so most of the, if I have a bag of 100 carbon atoms, 97 of them are going to be carbon-12. So they're very, very, very abundant. Very abundant. Okay. Hyphen notation. So know the difference in how to write hyphen notation and the nuclear symbol. This is hyphen notation. What has to be in hyphen notation, Bryce? Bryce? So again, in hyphen notation, there must be a hyphen. Okay. Now, how do we write it? Well, it's the element name. Okay. If it's oxygen, if it's uranium, if it's whatever. Okay. It's the element name and a hyphen. And then the key here, guys, make sure you get this. That it's not the protons, it's not the neutrons, it's not the electrons. It is the mass number. Make sure you get that. Yes, ma'am. Oh, yeah. So instead of it being carbon-12, it's just C12. Perfectly fine. Same exact thing. I mean, because I think one on the test y'all saw was sodium, 23 maybe, something, or 22. That was what was on the test. So really, honestly, remember what we say, chemists are lazy? Set it right in the hole where we put the symbols. Same concept. Okay. So no matter what you see, it's the exact same thing. Now, nuclear form, or the nuclear symbol. This is the nuclear symbol. Remember, it's that AZX model. So if you see this, don't freak out. The A is the mass number. Okay. And the key here, one of the things is that it's the larger number always goes on top. The smaller number always goes on bottom. That's an easy way to remember that one. So larger over smaller. So mass number over atomic number. And then X is just whatever the element is. So those are two examples on the right-hand side. So you can have carbon-12 and a number is 6, and then oxygen is 16. Will they always be half of each other? No. That's actually rare for them to be exactly half. Say that again? Basically, this is the format, okay? And then I just labeled that. Does that help? This is really what you want to focus on. The purple is what you want to focus on. And then I labeled the purple thing. That is the in the orange box is the nuclear symbol. Sorry, I guess I should have did a better job at explaining that. Yes, ma'am. It's on the periodic table. It is the single digit number on the periodic table. That's the atomic number. Or the whole number. Sorry. Not single digit, but whole number. Because all the other numbers are decimals. So if I ask, if I say what is oxygen, you'll look up it is number 8. Just like carbon is number 6. Okay, if I ask about neon, it's number 10. Lithium's number 3. So just look at whatever number it is. It's just an example. It's just an example. This is called the nuclear symbol. So if they ever ask you to write the nuclear symbol or identify the nuclear symbol, you would write it just like that. Okay. Yeah, I mean, it's a bullet. Yeah, you need to know it. It's the mass number. It's the number of protons plus the number of neutrons. All right. Next. Remember, I told you to kind of keep this in your head. Because the mass number is a whole number. The number on the periodic table for mass is a decimal. Where does that decimal number come from? It comes from the average atomic mass. And again, up there in the top right-hand corner, it's on the periodic table. It's on the periodic table. This is that number. So essentially, it's going to be a what? It's going to be a decimal, right? I want to try to cram this in here. Okay. It's going to be a decimal. I know that's written really weird. That's the best I could do. So how do they calculate it? Now, every atom has more than one isotope. Here's a hint. What were the 3 hydrogen isotopes? Very good. Protium, deuterium, and tritium. Deuterium. Now, what are the names based off of? It's not the number of protons, but it's based off the mass, right? Protium has a mass of 1. Du is 2. It has a mass of 2. And then tritium has a mass of 3. Okay, it's all about the mass. So what we do is we take the mass of the isotope of that element, we multiply it by the percent abundance. Now, what does abundance mean? Yeah, so if I have a bag of 100 of them, how many of them make up, or how many of them are in that bag? Okay. Now, if we have more than one, we're going to do that math and then add all of those numbers together. Good thing is you are not responsible for the math of this. I want you to know this. I want you to know the definition. It's all about this right here. It's all about the isotope and all about the percent abundance. That is your key. It's all about the isotope and all about the percent abundance. So make sure you know those things right there. Any questions? Now, I just want to show you the math so the definition makes sense. So, if I have carbon 12. Now, somebody asked me earlier, how do you know this? That is a knowledge of mine. You can look it up in a book. It's actually a known fact. Look, just Google it. It's out there, okay? No. Okay, but I want to show it to you. But this is how they did it. So carbon 12 is about 97%. So if I have a bag of 100 of them, how many of them are carbon 12? 97, okay? Carbon 13 is only 2%, and carbon 14 is 1%. So if you go back and look, right here, multiply the mass of the isotope by its what? Percent abundance. So let's look. Okay. Do you agree that 12 is the mass of carbon 12? Do you agree that that is the percentage? Remember, percent's real numbers? No, percents are not real numbers. You got to get them in decimal form. So multiply the mass by the percent, mass by the percent, mass by the percent, and then do what with them? Add them all up, and which is the last thing down here in black. Then add them all together. So when you do that, if you will look on the periodic table for carbon, it will be 12.01 grams per mole Mole is what we're getting to whenever you get back from fall break. So we're going to talk about the mole. Okay? You've been wanting to know what the mole is. You're finally going to get to it. All right, so that again is how you do the average atomic mass, and that's the number that's on the periodic table. All right, so let me clear this real quick. Okay, so if I want to talk about sodium, now, and I want to talk about specifically sodium-23. Yes, you need to write this. Definitely write this. This is one of the last bullets. Know how to solve for the number of protons, neutrons, and electrons in specific isotopes. So what is that 23 telling me again? That's the mass number. Very good. Okay. What form is this written in? Hyphen notation, right? Remember, what does hyphen notation refer to? It's the element and the mass number. Very good. You got to remember that. Now, how do I know how many protons sodium has? Where will you find that out? Periodic table. What number is sodium? Very good. It is number 11. Can you ever change that number? That's why I boxed it. Once you put it in the box, you got to leave it on. You can't get it out. Cannot ever change that. If it was neutral, how many electrons would you have? 11. Very good. You'd have 11. No, that's wrong place. Sorry. I wasn't paying attention to the location. So I'd have 11 electrons. Okay, I told you. Hold that thought. I promise I'll answer it on the next one, okay? Where I'm going is this blue box to answer that question. Now, 11 protons, 11 electrons. How would I determine my number of neutrons? Okay, it's never always the same. It's mass number, what? Minus protons. So mass number minus protons. So how many neutrons would I have? 12. Very good. Now again, does that affect the charge or anything? The only thing it affects is the mass. Okay, so Kaylin, you asked, how would you know if it's neutral? Let's talk about that. It's either going to tell you it has a charge of this, or it's going to look like this. So if all of a sudden I then say, okay, what if I had a sodium atom that had a 1 plus charge? Okay. Do you agree that this is not neutral? Okay. The way you can tell is because it has a positive. Okay. Or vice versa. What if fluorine, and I'm doing this for a reason, had a negative? Do you agree this is not neutral? Okay. Now let's talk about this. So now, can you ever change the number of protons? Never, ever, ever. So sodium is going to have 11 protons. Now, when you have a positive, that tells me you have what? You have more what? You have more protons. Now, how many specifically? One more. So what is my number of electrons? 10. Very good. You guys, there are 3 or 4 questions that deal with that. You need to be able to do that. Very, very simple. Okay, very simple. Now let's do the other one. Let's do fluorine. Now, what number is fluorine? It's 9. It is number 9. Now, since I have number 9, I have a negative charge. So it's when it's negative, that means you have more what? More electrons, more negatives. How many more specifically? One more. So it is very good. It is 10. Or is anybody confused on how to do that? Okay. Know how to determine the charge of an atom based on the number of electrons. Okay. So what if I told you this? What if I told you that I had an iron atom with a 3 plus charge? Okay, this is the question. You have an iron atom with a 3 plus charge, and we can look for 2 things. We can look for number of protons, and we can look for number of electrons. How can we easily find the protons? Look at the periodic table. What number is iron? First of all, what letter is iron? Fe, and it's number what? 26. Very good. Okay, so it's definitely number 26. Now let me pick on somebody. Nobody blurt this out. Okay, Mr. Seth. Since it is a plus 3, what is that telling me? Okay? Can I change this number? Can I change the number of protons? No. So what do I have to change? So how many electrons do I have? Very, very, very good. Does everybody see what he did there? Since you have a 3 plus, it's got to change the number of electrons. Any questions? Okay. I'm going to erase this. Change iron. All right, let me change it to something else. Let's see what else we can get. Something like that, yes. What if I have a nitrogen, and now it's a 3 negative? So, Christian, what is my number of protons for nitrogen? Somebody help him out. What number is it? It is number 7. Okay, so where's that going to go? Protons, okay? So since I have 7 protons with a 3 negative, how many electrons?
I'm sorry, 10.
Okay, what's right? 4 or 10? It is 10. Okay? Now, again, 3 negative tells you have 3 more electrons. Well, now do you have 3 more electrons? Yes. Okay, any questions? Let's look at the very last bullet. Know how to determine the number of electrons based on the charge. It's kind of what I just did. Determine the charge. Okay, that was the last bullet. Sorry, I need to go back to the one before. Know how to determine the charge of an atom based on the number of electrons. Okay. What if I have a zinc atom, and this is the second to last bullet. A zinc atom with (28) electrons. Okay, hang on. Got to think for just a second. Alec, first of all, number of protons, please, sir. Yeah, for zinc. Somebody help him out. Tell him what number it is.
30.
So where's 30 going to go? Protons. Okay. Now. Yeah, I had 20. Very, very good. So I have 28 electrons. So my zinc is a 2 plus. Any questions? Okay. So again, there's going to be questions just like that. Let's look at another one. Just kind of. All right. Let's look at. Okay. So this is going to tell me I have 18 electrons. So Bryce, sulfur, what number is it? It's letter S. 16, okay. So, what is my charge of sulfur? Okay, very good. Does everybody see how to do this? Does it matter what sign the negative goes on? So, since there's 2 more negatives, it's a 2 negative charge. So, are ions easy to do? Very, very, very simple. Guys, one of the next chapters we're going to get into is we're going to get to where you don't even have to think about it. It's all based on its group number. Okay, every charge is based on its group number except for the transition metals, and we're going to teach you those because you've been learning those group number transition metals. Does anybody remember what copper was? It had 2 of them. Okay, very good. What about iron? Very good. Iron is iron 2 or iron 3. And last one, lead. PB. Very good. Lead 2 or lead 4. And again, those are called transition metals. What does transition mean? They change. Do you agree those are changing? Yes. That's where we're going with that concept, that idea. But again, we will get to where how you did not even have to look at sulfur's periodic table. You can look at the group number and guarantee to know that it is a -2. And we're going to get into that in one of the near future chapters. Okay. So again, I'm going to send this video out. And if you want to watch it, watch it. This is not worth bonus points.